Working. So Jonathan Roberts from Rolls-Royce, expert there, who will talk about cyber risk assessments framework.
Thank you very much.
Thank you.
So I'm John Roberts. I am from Rolls-Royce, and I'm inspired to tell you, after a few lunchtime conversations, that for any of you expecting me to talk about the automotive industry, I can't. We don't make cars anymore. We leave that to our friends in BMW. So we're very much in the business of civil aviation, defense aviation, nuclear power, basically everything but cars now. So I'd like to talk about this thing that we've put together called the Cyber Risk Assessment Framework. And we've got some goals. Why did we do it? Why have we put this thing together? Well, we wanted an innovative approach to exploring the security impacts to safety and how a breach of your security system might directly impact your safety of the system. And I want to hopefully convince you today that security does indeed have a very significant role in resiliency and reliability of systems important to safety. So what's the relationship between safety and security? Well, I went and had a look on the internet, and I've drawn 3 models of what the internet says these things look like. Here's the first. 2 entirely parallel streams that don't really talk to each other and just sit in their own domains doing their own thing. Safety as a whole with a subset that is security. Now, in truth and honesty, I've actually seen this drawn the other way around as well, where safety becomes a subset of security, but no one seems to agree on that at all, so I left that off this diagram. And we've got this interpretation as well, where we've got security and safety as their separate domains, but coming together at certain points somewhere in the middle. Okay, this is the only one bit of audience participation now. I'd just like a show of hands. Who agrees with this model? Good, no one.
Current practice or target state?
I just want to think about what people think of how they are today. So I'm glad no one's. You're saying they're entirely separate things. Wrong. Anyone for the middle? Anyone for the end? Okay, so the vast majority of the room's going towards that, and that's kind of the model that we've sort of agreed on. So I'd like to take you through a brief case study. Now, the first thing we can conclude from this case study is that I'm a cybersecurity guy and definitely not an artist. So this should represent a mobile oil drilling platform. Now, this was out in the Gulf of Mexico, and we only have details from a Coast Guard report of what actually happened. So details, I'm afraid, are a little bit limited, a little bit sketchy, but it really does illustrate a point. So this thing is sitting out, floating away on the sea, and it's controlled by a whole bunch of systems, keeping it in position, doing its drilling into the seabed, and it's happy. Now, some maintenance was required, so one of the maintenance engineers on board took his maintenance laptop that we think he'd probably been using to browse the internet as well, and had picked up a banking card Trojan and plugged it into one of the controls, which immediately infected it. Now, the Trojan that was on this laptop wasn't interested in mobile oil drilling platforms. All it wanted to do was steal credit card details. And if it couldn't find some to steal, it would replicate itself and send versions of itself across the network as fast as possible. And it did. And it did it very rapidly, so much so that it flooded the whole control network, and the poor old platform didn't know where it was anymore, lurched wildly to the left, and ripped the oil pipe out. Now, fortunately, safety systems kicked in, and no oil was spilt. I think it's a really good illustration of how something as designed to steal credit cards managed to take down a control system of an oil platform. So how do we go about putting this cyber risk assessment framework thing together? Well, I went back to Google and we had a look what was out there already that could tell me about the relationships between safety and security. And we found this. This is by a chap called Firesmith. This is a subset of a much larger model, but this was the interesting part for me. So we've got this thing that's an asset down the bottom, and that's the thing that you kind of want to protect as part of your system. But the really interesting thing to me is this little bit down here, where we've got the danger can lead to an incident which can harm your asset. And in the model, it's saying that a danger can either be a hazard or a threat. Now, a hazard is something that's been talked about a lot today, and that's all to do with the safety domain. Whereas this idea of a threat is very much security domain. But Firesmith's saying that they're very similar. They both present a danger to your system. Whereas a hazard can lead to an accident, a threat is kind of like an attack. Well, it can lead to an attack, sorry, which is the incident that causes harm to an asset. So Firesmith's proposing here that both safety and security are somehow linked in a way. So I just want a quick note on hazards and threats, as we've just discussed. As we said, that hazards are very much associated with safety, and threats are very much associated with security. Now, I'm about to say something that's going to really upset safety purists in the room, so please bear with me. We generally think that hazards are derived from historical data, and we can put some form of probability to them. For example, mean time between failures. Okay, nobody looks too upset. That's okay, that's good. Threats are really difficult to predict. When is an attacker going to try and attack your system? It's tough. It's tough to look towards what we like to call a threat landscape to figure out who's going to attack you and when. So we've borrowed this idea of how we can put together cyber risk and how we can think of risk in terms of security rather than safety. Now, this is the slide I get questioned on the most, because I like to point out now, this is some real pseudo-maths. It's just to illustrate a point. Please don't take this as literal maths, otherwise you'll question me no end at the end of all of this. So, what are we saying a risk is in terms of cyber risk? Well, it's a threat multiplied by a vulnerability multiplied by a consequence, which the real part of the maths I want to show you here is these multiplications. What I'm trying to say here is, if our system does not have a vulnerability, this reduces to 0, so our risk goes away. And if there is no threat, our risk reduces to 0, so it goes away. It's just the idea of we need all of these three components, and if any of them's taken down low enough, then our risk goes away. But what's our threat made up of? Well, this is capability, which can be the sort of resources available to our attacker, his intent, why does our attacker actually want to attack, and opportunity, the conditions required for the attack to be successful. And this is an addition. This is saying that the more capability an attacker has, the greater your threat's going to be. The more intent and opportunity and so forward is the greater that threat is going to be. And that's my pseudo-maths. So we had a great starting point of this idea that threats and hazards are very similar, and we wanted to start putting it all together. Now, I don't like reinventing the wheel, so we wanted to find ourselves a good risk management methodology. Now, I've got an awful lot of slides to go through, so I won't tell you about them all, but we really favour this one from NIST, the National Institute of Standards and Technology. And they provide us a really great foundation for the start of this cyber risk idea, because they've got a nice risk assessment process, and more importantly, they've got this idea of a risk model. And we'll have a quick look at those both. Risk assessment process, there's nothing particularly exciting in here, I'm afraid. Identifying your threats and events, identifying your vulnerabilities, identifying your likelihoods and impacts to determine the risk. Cool. It's the kind of thing everybody's seen before and is used to. This was our favorite part, this generic risk model for cyber threat. Because we start talking about, threat sources initiates threat events, which can exploit vulnerabilities in the system that have an adverse impact, cause risk. Brilliant. That almost looks similar to the Firesmith model we saw at the very beginning. This looks a very promising standard for us. So let's try and dissect this a bit more. Let's have a look at these threat source things. What's a threat source? Well, this is the person or organization that desires to break your system because they're going to benefit from it in some way. It is not, like a threat actor, the person who actually performs the attack. Now, in a lot of cases, the threat source and the threat actor can be the same individual, but it's important to remember that there is a distinction between the two, particularly if the threat source has a lot of cash to hand, doesn't want to take a huge risk, and is more than willing to pay a threat actor to do it for them. Now, I'm not going to labour this slide at all. As they were going out to you guys, I thought it would be nice to give some ideas and examples of what threat sources and threat actors are. Yep, I'm sure you can read them all in your own time. There's nothing I particularly want to pick out of there other than to say that, yeah, unfortunately in the news we're seeing ever more sort of foreign intelligence services and organised criminal groups paying off our threat actors to perform these kind of attacks. Threat events. So, back to NIST. They gave us a huge amount of threat events to look through, an absolute gigantic list, too big, in fact, to be useful. And we want to make a very generic framework to start looking at how these threat events fit into the rest of our world. So we wanted to pick something much more manageable. And Microsoft produced this threat model called Stride, and it fits our purposes perfectly. It has 6 things: spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privilege, making up the acronym STRIDE. And I'll talk you through those now. So, consider this as a normal, everyday system. Just 2 simple nodes communicating in some way. These could be 2 PCs on a network, for example, passing some information. And that's its normal, happy day scenario. Spoofing, the S of our Stride. This is where an attacker will try to make his node look awfully like the source node to pass disinformation to the destination. So a great example of this is, I know I've received, and I'm sure a lot of you have, received an email that looks like it's from your bank or insurance company, that looks awfully like it's from them, but on slightly closer investigation, you can tell it's not, and they want you to click on a link. Yeah, that's a classic sort of spoofing attack. Tampering, man in the middle. Somebody sits in between this communication from the source to the destination, modifying the traffic that's coming through. A great example of this is malicious actors taking a high-powered router, for example, throwing it in a rucksack and going to the local coffee shop, pretending to be a genuine access point in that coffee shop. You guys logging on to that Wi-Fi router where all of your communications can be intercepted and manipulated however that attacker feels fit. Or he could have taken it to a conference, for example. So thanks to everybody who's logged onto the conference Wi-Fi today. It's going to pay for my night out later. Thank you. Repudiation, a horrible word. I'm very sorry for this one. It comes from law, civil law, to if you repudiate on a contract, it means you're unwilling to fulfill the terms of that contract you said you were going to. So that roughly translates here to claiming that you've performed an action that you haven't, or claiming not to perform an action that you have. And the typical example is using to falsify orders or commands, or altering logs around systems. So if I wanted to move £500 of money out of somebody's account, I want to clean up afterwards to make sure it was never me who did that. Information disclosure, having a snoop between the source and the destination? What packets of Wi-Fi can we sniff in between those? What data's been transmitted from that webcam that's completely open and that I can see? And denial of service, loss of function. Denial of service has got in the news an awful lot recently. A great example is our mobile oil drilling platform. Because of that banking Trojan, it completely denied the control systems the ability to do what they were set out to do. And the hardest one to explain, elevation of privilege. So what this is, this circle represents an operating system, for example, with my kernel in the middle, and he has the most power to do everything and the most damage in the system. Now, I would typically expect my users to be sat out here using the applications, putting in a request, and then the application will pass requests down the chain where there's lots and lots of checks to make sure that if I've not asked it to do something I don't want it to do until the kernel can do something for me. Elevation of privilege is our intruder trying to sneak up these layers to avoid all of the checks so he can do directly dangerous things right in the center of the circle. The next part, vulnerabilities. So what are these? Well, these are weaknesses in the system that are used by the threat actor to perform unauthorized actions. So those 6 stride examples before, those are the vulnerabilities, those are the attacks that he's looking to exploit these vulnerabilities with. NIST provide huge amounts of list of vulnerabilities again, but this isn't something we're particularly going to add to our cyber risk assessment framework. This is for you guys to go and figure out what the vulnerabilities of your systems actually are. But they do put them into 6 high-level groups, which I've put here. Now, interestingly, when everybody talks about cybersecurity, it's always the sort of the hacking the software and the messing with the systems. That's kind of only really down here. It's always interesting to me that we never really think about vulnerabilities at policy and procedure level or even physical level, but they are really important. So I encourage you to go and have a look at those after. So, moving away from the bad guys, what do we want to protect? What are the attributes of our data items that are important to us? Well, typically when talking about security, we talk about this confidentiality, integrity, and availability, CIA. But we like to expand it a bit further to add non-repudiation, authentication, and authorisation. CIANA is the acronym we kind of like. And I'll take you through these briefly now. What is confidentiality? Well, we need to make sure with confidentiality that we're not leaking information. When I make a transaction on the internet with my credit card, I only want the bank to deal with that and nobody else in between. I like to keep my credit card information safe. Integrity. This is making sure that data traveling around is the actual data that we want to be traveling around. For example, let's say in one of our jet engines, we're using a complicated algorithm that is interested in the current temperature and pressure of our engine. Now, if it's making a huge decision on the current temperature and pressure of the engine, I really want to make sure that it really is the current temperature and pressure. I'd want integrity to be high to make sure we're doing the right calculations. Availability. Oh, to do these calculations, I actually want the data there as well. That's kind of important. I need data to be available and on demand when I require it. Non-repudiation. The astute of you will notice this is an even more horrible word and is absolutely the opposite of repudiation. So it's proving something that has happened when it has and just didn't happen when it didn't. Authentication. I want to make sure that when I use my credit card, that it's me using my credit card. I've got a PIN number that I can use to authenticate that it is indeed me. And authorization. Making sure that the person who's trying to do something does indeed have the authorization and privileges to do that thing he wants to do. Sorry for the dreadful reference. The Wikipedia, the definition was the best one we could find. So, this is where our framework starts to build. We have these stride things, that these are what our attackers are trying to do to our systems. And we have these Sienna properties of our data that we want to hold and make sure are safe. But there's a link. Spoofing undermines authentication. Tampering directly undermines integrity. Repudiation, no prizes for this one, directly undermines non-repudiation. Information disclosure, confidentiality, denial service, availability, and elevation of privilege, authorization. So we have a link. We've shown that what these kind of attacks undermine these kind of data security properties. Moving slightly away from our cyber world now, I'm going to move into the safety world. Now, the Safety Critical Systems Club kindly did some data safety guidance work a number of years ago now. And this contains a number of data properties, the loss of which present a hazard to a safety system. So what they say is, if I lose consistency in some types of data, this can present a safety hazard to our system. Be careful, integrity and availability are up there. The R's are not the same as the availability integrities we've just talked about. This is a data security world. Sorry, a data safety world. I'm mixing them up myself now. This was really useful for us, and this is where we put a huge amount of effort into this framework. Because if we take our Sienna properties again, we have now put mappings saying that if we lose confidentiality because of an attack, then we might be losing the data safety properties, traceability, suppression, disposability, intended destination, and accessibility. And we went through all of these, and we've put mappings in to how security being undermined will undermine the safety of a system. Even more than that, thanks to the data safety group, we've got mappings from those safety properties to the world of HAZOPs. I'll show you an example now. So let's take this data security property, availability. We have a link directly to the data safety property, priority, which we saw on the previous slide. And we have a nice description saying that priority is the data presented, the data is presented, transmitted, and made available in the order required. If I'm doing a calculation on my temperatures and pressures that we alluded to before, I want to make sure that the current ones, not ones 10 minutes ago. We now have mappings additionally to these HAZOP data properties, where we can start asking questions like, if I have a loss of priority, what safety impact will that have to my system? If I have an incorrect priority, what safety impact will it have to my system as well? And for the HAZOP users out there, we also have a link to all the HAZOP guide words that you should be considering when priority is important to your system. So, I know I've provided an awful lot of information here, but I really just wanted to get to the point that we now have links between threat actors and threat types and vulnerabilities, threat types and data security properties and data safety properties and potential hazards. Whew. What did we do with it all? Well, this is where we built our cyber risk assessment framework. Now, I don't know if there's any modeling types in the room, but what we did is we kind of like SysML back at Rolls-Royce, so we've made a gigantic SysML model that contains all of this information. Now, I apologize, I'm sure a few of you are going to be squinting a little bit on here, but it's all to do now with Excuse me, I'm squinting as well. This is our system of interest that we're saying contains a bunch of vulnerabilities. And over here we have threat actors that can mount a threat type to information assets that may result in a hazard. Now, this is just a quick view of the top level of our model, but you can drill down into it further and further. These are just some comments, but this is the kind of thing you'll see inside of the model with our bystanders and handlers, our stride, our CANers, and all the data safety properties. So we have this cohesive model of data security, data, and data safety properties. So let's go back to my my mobile oil-driven drilling platform. Let's see how the craft could have helped with this example. So we can identify that what's really important to these servers on the oil drilling platform is this control signal. And we have a look through the data safety properties, and we think these are the ones that are important to this control signal. So in consistency, accuracy, availability of this control signal, that's all important stuff from a safety world. And then we can start thinking about the kind of people who may attack us. And this is a virus or other malware writer. He was picked from the list of threat sources. No, he's not the threat actor, though. He didn't actually initiate the attack. He's the threat source. Because he wasn't interested in mobile oil drilling platforms. He was just interested in acquiring credit card detail. The threat actor, by accident, was our maintenance guy. And we know that self-reproducing banking malware is all about confidentiality. It's all about the loss of your privacy of your credit cards. But because of the craft, we've also got a mapping to know that because it's a self-reproducing Trojan, that undermines availability as well. And we know, because of the craft as well, that availability will undermine the safety properties of sequencing, timeliness, and the safety availability. So hopefully you can see how this kind of analysis using the cyber risk assessment framework can take us from our original threat actor right down to the potential hazards that could have been caused by this. So how do you use it? Well, we propose it as a two-part problem. One, you need to scope your problem. So the first thing is, look at your system and identify the physical and logical boundaries and access points of that system. Identify your potential vulnerabilities. NIST give you a whole bunch of potential candidates you can look at. And identify the information assets. That's part one. Part two is actually using the craft. Identifying the threat actors and linking them to the types of threats that they can perform. Assessing the threat types against the potential vulnerabilities you've identified, and then for each vulnerability, assessing the impact of the threat type to the data and the security properties of each information asset in your system. And then using that, looking at the safety properties of your system and looking through your HAZUP guides, words, and properties that are presented to you. So where are our limitations on this? We've got a lack of validation of that bridge, the linking of the security to the safety world. We have not tested extensively. And this is kind of where you guys come in. This is not something we want to keep internal to Rolls-Royce. We're trying to roll this out for use in the wider community. We're working with the Safety Critical Systems Club to try and get them to adopt this and push it out into the wide world for you guys to use and see how you got on with it. There is a concern about the scalability of our data safety assets as well. In large, complex systems, you're going to have an awful lot of data, and to perform this could be an incredibly large task. We don't know how that's quite going to work out yet. And it's no replacement for common sense as well. We can give you a good structured way of how to do a risk assessment, but it kind of needs that little bit of engineering flair as well, and thinking outside the box. Just because you go through this process doesn't mean we don't think you're going to get the exact perfect result without thinking about the problem too. So I've convinced you today that security does have a role in resiliency of safety of systems, and we do have this thing, the cyber risk assessment framework, that we can help to understand that a breach in security can have impacts on safety of a system. And for those of you who are in my workshop tomorrow, you're going to be my guinea pigs to try and go through this a bit further and try and use the CRAF on a example. So, any questions?
Thank you. Okay. Thank you. In safety, we talk about risk reduction, getting to an acceptable level of risk. Is there some way here you can reason about, well, you had some analogy, but talking about the level of risk or assurance when it comes to security?
I removed the slides on this. If you think about it, the risks you identify throughout this process are going to become requirements on your system. So what we'd like to see is people using this to understand that the risk they have due to cyber to generate further requirements, so the system can therefore be modified to be resilient to those risks. But it's all about setting a risk appetite as well and what you're willing to accept.
Hello. Yes, good, it works. In your oil rig example, I can see how you could very easily identify the actor as the maintenance person coming on board, because that's a very common way of spreading viruses. How much further do I need to go back as to how his computer got infected? I mean, I probably wouldn't think about someone stealing bank cards, but is it any virus on his computer? Is that as far back as I need to go, or do I need to keep, in your methodology, keep working back and back and back as to different types of attack there?
I don't think. I think as long as you've got an appreciation that malware exists, and we desperately want to try and keep malware away from control systems, because it's a great example that they don't mix too well there. So. I'm going to have to think about that one a bit more, and I'd like to come back to you on that. But it's a good question. Yeah.
Can you go back to the slide where you showed safety and security Venn diagrams?
At least it wasn't the maths slide, so thank you for that.
That's the second point.
Oh, no.
So there's a point to these diagrams. If you take your middle diagram, there we go.
Here we go. There you go.
Great.
Yeah.
Safety and security. There is currently an effort on a standard, which is probably going to be a technical report, not a standard, called IEC 63069 for industrial control systems, that has that diagram with security as the outside ring, safety as the inside ring, and it has a lot of people, in particular in Germany, who have been putting that forward as the model for safety and security for industrial control systems for a few years. There are a number of people, and you're listening to one at the moment, who thinks this is a very bad idea indeed. I think it would be great if people could get involved and comment on that. There is a commentary process in the IEC, but it's hard to get at from within the British Standards Institution. But I might like to encourage you to try.
Yes, I wholeheartedly agree. I mean, on a very personal note, this is my personal feelings. As far as I'm concerned, security is a big world to me, but it always takes second place to safety. Safety always has to win. There is no competition.
The second point is about your math. Your math, I would say, is better than it looks, because what you have is an ordinal scale here. If you have no vulnerability, then you have nothing to worry about. If nobody in the world knows about a vulnerability, then you have very little to worry about. If somebody in the world knows you have a vulnerability, you have a little more to be worried about, but not a lot until that person has identified an exploit.
Agreed.
Then you have a lot more to be worried about. But you still don't have to be worried until the exploit is actually implemented. And when the exploit is implemented, you only have then to worry about who has it and if they're targeting you. So I would suggest your arithmetic is spot on, but you're doing it in terms of numerical arithmetic rather than ordinal arithmetic. It's an ordinal data type, and I think that's the way it goes.
Thank you. I appreciate that. I'll mention. I'll use that next time. So I won't call it pseudo maths. Thank you for your comments. Really appreciate it.
Any more questions?
You just all want an early dinner now, don't you? That's it. Thank you very much.
So thank you very much.